Welcome to Calculus 1, Chapter 3, Section 1, where we're going to talk about derivatives of polynomials and exponential functions. This section is really nice because this is where life starts to get a little easier. And what I'm going to show you in this section is how we start taking derivatives without having to go through the limit process. And these slides do include articulation on kind of the backstory of how we go from the limit process into this sort of shortcut process, if you will. I'm not going to get into the backstory. It'll be on the slides. If you want to pause the video and read some of these slides, you're welcome to. But I'm not going to get too deep into it. Some little comments here and there, no doubt. What we're seeing on this slide is the graph of y equals c, which is some constant. And as we know, the slope of a horizontal line is 0. The slope of a horizontal line is 0 everywhere, whether we choose to look at it at this point, which has an x value, or this point, which has an x value. The slope of a constant value, or the slope of a horizontal line, is 0, no matter what x coordinate we're looking at. And so that allows us to say that our first derivative of that kind of a function, where f of x equals c, is going to be 0. Because remember that the first derivative is all about rate of change, or another way to say rate of change is slope, or rise over run. Change in y over change in x. And y might represent dollars, and x might represent time, in which case it could be p of t, so p is price, where it's a function of time, and your horizontal axis is the t-axis instead of the x-axis. But regardless, the first derivative is all about rate of change, and more specifically, the instantaneous rate of change. And while we've seen this kind of notation right under me here, where it says f prime of x, and that prime, that little tick mark there, indicates the first derivative, another notation here in this blue box is d over dx. That's the rate of change with respect to x. It means that we're being tasked with taking the derivative, and here we see that the derivative of a constant function is 0. It doesn't matter what our constant value is, 0 is the derivative. By power functions, we mean where our variable is being raised to a power, and this is one of the instances where we're going to see more articulation of the backstory. You can explore that to whatever extent you wish. This first pretty basic example we have generally right at the top of the screen. We're now looking at functions where our variable is being raised to a power. This graph is where x is being raised to the first power, y equals x. And the slope of this graph, no matter what x coordinate we're looking at, if we go up to that point on our graph, we see that the slope of that function is 1. And so it appears that the first derivative of this particular function, f of x equals x, the first derivative of that function is 1 everywhere. What's f prime of 7? Still equal to 1, because the slope of that function is 1 when x equals 7, and 5, and negative a million. So again, talking about slope, talking about rate of change. So we can say that the derivative of the function x to the first power is equal to 1. Now, you've taken derivatives of functions like this before, except you did it the long way using limits. So you might remember that the derivative of x squared is equal to 2x, and that the derivative of x cubed is equal to 3x squared. We could go through the process of taking the derivative of x to the fourth using limits, and we would have to take an expression like this and FOIL it out, or use the binomial expansion theorem. and we get all of those terms, all of these, and then we cancel out that minus x to the fourth, and we get this, and then we cancel out a factor of h from all of those terms, and we get this expression, and then we finally get to send h to 0, and all three of these terms go away, leaving us just with 4x to the third. I wish there were a faster way to do that. Good news, there is. Here's the power rule in this horizontal box, and then somewhere down here there's the power rule general version. I'm not sure that I can see the difference between the two, x to the n, and this says x to the n. So these are identical, and we'll use this one. What this says is that if you're taking the derivative of x to the power of n, the derivative is n times that variable, which is x in this case, to the power of the previous exponent minus 1. All right, so again, this exponent has appeared in front of the variable. There it is, and the exponent has been decreased by 1. Let's see some examples of that. In part A, you see the original exponent of 6, and then you see that 6 is appearing now as a coefficient, and the previous exponent of 6 has been decreased by 1, now it's a 5. In the next example, the 1000 has become a coefficient, and the exponent has been decreased by 1, and so on and so on. Does it work for different variables? Yes, here we're working with the variable t and the variable r. It still works. Well, so far I'm really liking the fact that taking the derivative has just gotten considerably faster. And you're going to be doing that in your homework assignment. This is more of a, I typically see normal lines in physics problems, but you could run into an applied problem in just in your Calc 1 course. But in a physics course for sure, you should know that a normal line is the line that is perpendicular to the tangent line. And you'll see that in centripetal motion, or if you have a car that's driving around a curve, you'll have to look for a normal force, which is perpendicular to the direction of motion. And remember that if the slope of your tangent line were 5/2, the slope of your normal line would be -2/5. Remember that perpendicular lines have slopes that are opposite reciprocals. We saw a rule a lot like this when we were working with limits and taking the derivative. If there was a constant multiple inside of our limit, we were allowed to factor that out. And here we're seeing that we're allowed to factor it out of the derivative process using this shortcut process. So here the factor of c is now appearing outside of the derivative process. We would take the derivative of f of x, get some kind of a result, and then multiply that c value, that constant value, back in. Let's see some examples. So here we're taking the derivative of 3 times x to the 4. You can see that 3 has been factored out of the derivative process. We take the derivative of x to the 4. The 4 comes down in front of the variable. So you see the 4 here now. The exponent has been decreased by 1. It was previously a 4. Now it's a 3. And then, now that we've completed that process, we can take the 3 from in front that we had factored out, we can multiply it back in, and that gives us the 12. Another way to think of this process is simply taking the original exponent, multiply it immediately by the leading coefficient, which gives you the 12 right away, and then take that original exponent and decrease it by 1. So the 4 minus 1 would give you a 3. Let's try that thought process on this next problem. Ooh, I don't want to do that one. Yeah, I suppose it's a good idea to realize that if you have a negative in front of your variable, that is essentially a multiple of -1, and you could factor that out of the process. So negative x is definitely the same thing as -1 times x. Now that -1 looks more like your typical coefficient, so it can be factored out front. Here it is. Then we take the derivative of x. And remember that y equals x is a line with a slope of 1. So the derivative of x was equal to 1. And there it is. And then -1 times 1 was -1. I don't know. Oh, this happened to me once before where my iPad started blinking in and out. Let me try unplugging and replugging. Sorry about this. See if that'll bring it back in. There we go. We saw a rule similar to this when we were working with limits, that the limit of a sum was equal to the sum of the limits. Here we have the derivative of a sum is equal to the sum of the derivatives. So it is as though we are distributing the derivative process over a sum from term to term. And we can extend that process to as many terms as we'd like. If there's subtraction involved, we're being told that you can think of that subtraction process as adding a term that has a coefficient of -1. What that allows you to do is to really strictly apply the rules of the derivative process as you go from term to term. We don't typically think of it that way, but what it allows you to do is change subtraction into what it really is, which is the addition of a negative number. And so if you're now using addition, then this difference rule that we're seeing on this slide is really the same thing as the sum rule. Did they call it the sum rule? Yeah, the sum rule. The only difference is that you're adding a negative number, so you have that coefficient of -1. But otherwise, it's the same. You can still distribute over subtraction. And then we see the beginnings of a conversation about exponential functions. And let's not compute the derivative of the exponential function. These are the kinds of things that if you want to pause and check them out in some detail, you can read through this. What I'd like to do is really sort of get to the heart of it and make sure that you are prepared to take the derivative of exponential functions. And exponential functions, remember, are functions where the variable is in the exponent position. So here they're taking the derivative of 2 to the x and 3 to the x. And we're going to see more of that in a later section. I think it's 3.4 where we see that again. We'll get to it. Here's the definition of the number e. That's nice. Right, you can check that out. And finally, after all the backstory, we arrive to the derivative of the natural exponential function. So if we take the derivative of e to the x, the result is e to the x. You can see why I didn't want to spend too much time on the backstory, because it's a little anticlimactic to go through like 3 or 4 slides worth of content and going back and revisiting limits just so that you can arrive at a point where the derivative of e to the x is e to the x. Now, when we get to section 4, I believe it is, where we talk about the chain rule, we're going to change the x in the exponent position, and we're going to make that exponent more complicated. And then this definition, so to speak, becomes a little bit more involved. Nothing you can't handle. So let's glance at this example here. We're taking the derivative of e to the x minus x. This property that says that we can kind of distribute the derivative process from term to term allows us to write that we're now taking the derivative of each of those terms. And the derivative of e to the x, as we just talked about, is equal to e to the x, and we've already mentioned that the derivative of x is equal to 1, and so our solution for that problem is e to the x minus 1. A second derivative is simply taking the derivative again. So if we take the derivative of the result that we got in the previous example, e to the x minus 1, if we take the derivative of that, we can distribute the derivative to both terms, and then taking the derivative of e to the... I hate when that happens. Sorry. I click too fast and it just takes me flying back to the beginning of the notes. First derivative, second derivative, here we go. Then the derivative of e to the x is still e to the x, but now instead of taking the derivative of x, we're taking the derivative of 1. 1 is a constant. The graph of a constant is a horizontal line. Horizontal lines have a slope of 0, so the derivative of a constant value is 0, which is why we're seeing our final answer here is e to the x, not e to the x minus 0. We've gone ahead and left that out, but there is a minus 0 at the end. We would never write that, though. So an example of a pretty simple second derivative. And that is the end of the notes for this section. I'd like to pop over and look at a homework assignment. There are just a couple of other variations of these types of problems that I thought we could check out together. So here we're taking the derivative of this function 2 to the 30th power. What is 2 to the 30th power? Oh, I've gone ahead and printed this homework assignment to a PDF with solutions. But I don't want the solutions to be on the screen. I want to be able to talk through the process on some of these problems with you. So I'm going to pause real quick, reprint this to PDF without solutions up, and then we'll start going through these. Okay, here we go. So in this example, or in this first problem, we're taking the derivative of 2 to the 90th power now. And 2 to the 90th power is just a number. It's a really big number. But whether you're taking the derivative of a constant value that's small or a constant value that's large, the slope of that graph is still going to be 0 everywhere. And therefore your first derivative will be 0. Differentiating this function, you're going to take the derivative of the entire right-hand side of this, take the derivative of the first term, take the derivative of the second term. It might be helpful for you to think of this t as having an exponent of 1 on it, so that you can take the exponent, multiply it by the coefficient, decrease the exponent by 1. In which case the derivative of 5 is equal to 0. I'm going to bring down the minus sign. I'm going to take this exponent of 1. I'm going to multiply it by the existing leading coefficient, or the existing coefficient, 2/3. So 1 times 2/3 is 2/3. I'll keep the variable, and then I'll decrease the exponent by 1, which makes it an exponent of 0. Anything to the power of 0 is equal to 1. Therefore, this really says 0 minus, so it's just negative, 2/3 times 1. Well, really, that's just negative 2/3, because t to the 0 is equal to 1. So in this problem, my answer would be negative 2/3. Another way to think about this, and being able to very mechanically go through and look at the derivative term by term is a good skill, because there are definitely problems where you're going to want to do that. But in these introductory level problems, it's also good to keep an eye on what's really happening. This function that we're looking at, 5 minus 2/3 t, could just as easily be written y equals negative 2/3 t plus 5. That is the equation of a line in y equals mx plus b, or slope-intercept form. And we know that in that format, the slope of this line is negative 2/3. When is it 2/3? All the time. It's a line. It consistently has a slope or a rate of change of negative 2/3. So it's no surprise that the derivative of this function is a fixed value of negative 2/3, because its rate of change, or its slope, is always negative 2/3. Now this function is not a line. This is some extreme parabolic looking kind of a graph. X to the 10th power. Plug a couple numbers in there and see what you get, right? Plug in a 0, you get 2/5. Plug in a 1, you get, plug in a 0, you get 0. Plug in a 1, you get 2/5. Plug in a 2, and now you've got 2/5 times 2 to the 10th power. And 2 to the 10th power is 1,024. Then you have to double that and divide it by 5. Still a very large number. So this thing has y values that are increasing very fast. So the slope of a tangent line, especially once you move outside of your y values of positive and negative 1, the slopes of those tangent lines to this curve are going to be big, either very positive or very negative. But let's look at the mechanical process of taking the derivative. We need to take the exponents of 10 and multiply it by the leading coefficient. So that is 10 times the 2/5. Then we'll keep the variable, and we'll decrease its exponent by 1. So whether you want to write 10 minus 1 or you want to put a 9 there right away, I leave that up to you. And then we'll simplify this a little bit. The 10 divided by 5 reduces to a 2. 2 times 2 makes 4. And there's our variable to the 9th power. Or if you'd rather do these by taking limits using the difference quotient and sending h to 0, you're welcome to do that, but I'm finding this to be a much more enjoyable process. I hope you are too. You might be a little bit upset that no one told you that this shortcut existed earlier, but be happy that you're aware of it now, and the study of calculus does require that we learn the backstory and the use of limits. Now you're aware that it's there, you can say that you have survived that process, and then you're rewarded with these kind of shortcuts. This problem is the same, just go term by term, take the derivatives. Remember that this is a linear factor, so its derivative in this case would just be 7 or negative 7. This is a constant value, derivative of a constant is 0. Now this problem, I did want to look at this one because in the next section, in 3.2, I'm going to teach you something called the product rule, which is useful because what we really have here is a factor times another factor. They're factors because they're connected by multiplication. And when you have the product of two factors and you need to take the derivative, there's a rule called the product rule, which allows you to more easily take the derivative of a product. In this case, however, 1, we haven't talked about the product rule yet, and 2, if I had to take the derivative of this, which I do, I would just distribute multiplication by x squared. Even if I knew the product rule, which I do, I still wouldn't use it. I would just distribute multiplication by x squared to these two terms and get x squared minus 7x to the third, and then take the derivative of that. Multiply the exponent times the coefficient, decrease the exponent by 1 for both terms. Okay, so I'm going to leave the rest of that up to you. Take the derivative. These instructions say differentiate. That means take the derivative. Okay, we can do that. Oh, this is interesting. We've got different function names. It's capital B. We've got different variables. Our independent variable here is y. This has a leading coefficient, but we don't know what it is. It's some undisclosed constant value called c. Doesn't matter. We're going to use the same process. We'll take the exponent. We'll multiply it by the leading coefficient. That's -2 times c. We'll keep the variable of y and we'll decrease it by 1. Decreasing by 1 means subtracting 1. -2 minus 1 is -3. Don't be giving me answers of -1. I don't want to see an exponent of -1. Make sure that you're going in the negative direction, so that made it -3. And then there's nothing you could do to clean this up except for maybe take this multiplication symbol out of here that I had put in. If my eraser will work, get in there. Oh, I erased part of the c. And I touched something which moved me around the screen. Okay, so -2c times y to the -3rd, that's it. That's your derivative. Until somebody tells me a c value, this is as good as I can do. All right, it's an unusual answer, but it is the answer. Find an equation of a tangent line. You've done these problems already. Remember, please, that when you're designing the equation for a line, it's very typical to start with point-slope form, which is y minus y1 equals your slope of m times x minus x1. In this problem, they gave you x1 and y1. They did not, however, give us the slope. In order to figure out the slope, slope is synonymous with instantaneous rate of change, which is synonymous with take the derivative, and probably plug in an x value. In order to find the slope m in this problem that you need in order to create the equation for this line, you'll need to take the derivative of your given function and evaluate it at a particular x value. This x value. So you're going to need y prime evaluated for an x value of 1, and that's going to be the slope of your line. It'll still be in point-slope form, so you're going to have to do a little bit of arithmetic, distribute, and solve it for y, because they want the answer in y equals mx plus b form, or slope-intercept form. You can handle that. But most importantly is realizing that you need this format for your line, and you need to plug in the necessary information. x1, y1, and you'll have to calculate your m value by taking the derivative and plugging in your x value. You can do it. Find the equation of a tangent line. Again, so just a slightly different function. You're still being given a point. That's nice. If you run into a problem where you're not given the y value, if you take the number 1 and plug it into your original function, you would find that you get a y value of 5. So it will happen from time to time that you're not given this y value, and you'll have to figure it out for yourself by taking the x value and plugging it into the original function. Then when it comes time to find the slope of the tangent line, you'll have to take the x value and plug it into the derivative of the original function. So the original function outputs y values, and the derivative of the original function outputs rate of change, or slope of tangent line, at a particular x value once you plug an x value in. And then you're matching it up to a graph of the curve with the tangent line drawn on it. You could use a grapher to get that, or some of these tangent lines look pretty similar. You should be able to use end behavior also in order to determine which of these curves is the correct curve. Just a quick reminder on end behavior. This original function y equals, if I switch my terms around, I would write it as y equals -x to the third plus 6x squared. This is a polynomial of odd degree. It's a third degree polynomial, and it has a negative leading coefficient. So the graph of y equals x to the third looks like this. It falls to the left and rises to the right. However, y equals -x to the third rises to the left and falls to the right. So just a quick reminder of some of the discussion about end behavior of polynomials. And the only reason that's beneficial here is because it would help you narrow it down in choosing the graph of the correct curve. The upper two rise to the left and fall to the right. These two curves down here fall left and rise right. Find the points on the curve where the tangent line is horizontal. You want the slope of your tangent line to be the same as the slope of a horizontal line. In other words, you want the slope of your tangent line to be 0. So you're going to take the derivative of the given function and you're going to set it equal to 0. And then you're going to solve, and you're going to get two x values. The smaller of your x values is going to go here. The larger of your x values is going to go here. But we're being asked for points on the curve. You got the x values of the points on the curve where there is a horizontal tangent line. You now need the y coordinates of those points on the curve. So you'll need to take your x values, once you found them, from using the derivative and setting it equal to 0. You'll take those x values and plug them back into the original function in order to find the y coordinates. Remember, your original function outputs y values. Your derivative outputs slopes of tangent lines, or rates of change. The derivative of this function you can handle. The reminder is that the square root function is the same thing as raising to the power of 1/2. You will still take the exponent, multiply it by the coefficient, and then decrease the exponent by 1. And I mean literally the exponent minus 1. I'm sure that you can do 1/2 minus 1, so I'm going to leave you to it. Should I leave you to it? You're going to have to discover on your own whether or not a negative exponent will be accepted in here. I am going to go ahead and start working on this derivative actually, because we'll have the 1/2 as the exponent multiplies down times the existing coefficient. We'll keep the variable, we'll decrease the exponent by 1 so it becomes negative 1/2 minus 3 times the derivative of e to the x is e to the x, as we discovered. We read that. And then I would write this coefficient up here as 3/2. And then the question is, can I leave this as x to the negative 1/2 power? X to the negative 1/2 power is equivalent to 1 over x to the positive 1/2 power. And x to the 1/2 power is the same thing as the square root of x, so now this is 1 over the square root of x, which, am I supposed to rationalize my denominator? I don't know, it's not an algebra class. Multiply by the square root of x over the square root of x, and you get the square root of x over x. So we have rationalized our denominator. Is this what you're supposed to be using here? You'll have to experiment and find out. See what your online software will let you get away with. We're going to want to make some modifications here before we start the derivative process. I would change this to, well, just as a reminder, the cube root of x is the same as raising x to the 1/3 power. I still don't want to take the derivative of this with my variable in the denominator. So I would rewrite this one more time with a plus 4x to the negative 1/3 power. Now you're in a better position to take the exponent, multiply it by the coefficient, and decrease the exponent by 1. Once you decrease this exponent by 1, you're going to have a power of negative 4/3. You're going to have to experiment with how the software will allow you to enter an exponent of negative 4/3. Or do you have to make it positive 4/3 and push it into the denominator? But go through term by term and take the derivative of that stuff, and that is it, ladies and gentlemen. That is 3.1. This ought to give you a really good start on the process of using these new tools for taking derivatives. In the next section, we're going to use all of these same tools that we saw here, but we're going to combine them with our conversation about the product rule and the quotient rule, which is going to help us take derivatives of slightly more complicated functions and expressions. So I'm going to head over there. See you there. Thanks.